Okay, hello. So good morning, Adriano. So in this case, we're going to talk about molecule shapes for those of you who missed out a while ago. So these are the questions to be answered, and I know it sounds very intimidating, but we will get through it along the way. So first, what is VSEPR? It's your valence electron pair repulsion theory. Now this means that there are certain valence electron groups that are actually around the central atom. Now, the thing is that because they are electrons, they tend to repel against one another, therefore creating unique shapes, generating maximum space, and of course, they start to create unique shapes, and that we can actually categorize and have certain theories apply to these compounds, rather molecules. So just to take note, there are certain rules that we have to follow. First is that lone pairs, again, are non-bonding, so we can't really form bonds with other atoms because they are lone pairs. And of course, we also have your bonding electrons, which are the valence electrons that are shared between the atoms. So just like right here, the green ones are your bonding electrons. So this is shared between oxygen and hydrogen. Then the light blue ones are your lone pair electrons. And eventually, it actually forms a structure that looks like this if we follow your VSEPR theory. Now, we'll get into that as to how to form these shapes in a little while. So first, we have to follow our configuration. So we will call this as our Axmen. Okay, that sounds German. We will call this as your Axmen configuration. First, what is the A part? Okay, let me just move myself. A is actually, if you would look down there, A is your central atom. If you would look over there, X is your it's the number of atoms that are bonded to the central atom. So we're going to talk about that a little more later on. And then the subscript for E would be the number of lone pairs around the central atom. So again, the first thing that this first skill that you need to do is first, of course, to identify which are your lone pairs and which are your shared electrons. And of course, you also should be able to determine how many atoms are attached to the central atom. And of course, how many lone pairs are there in the structure. So I'm gonna move myself again down here. So if you would look here, these are actually some of the shapes that are present in your VSEPR theory. So some would be linear, some would be trigonal planar, some would be tetrahedral, some would be bipyramidal, some would be octahedral. And of course, it all depends on the structure of the molecules. So I have this example right here. This is linear. If you would notice, A is the central atom, right? E is represented by these balloons that have two dots signifying the lone pairs. And of course, the black, the grayish circles right here are your surrounding atoms. So they are the ones connected to the central atom. So if you would look here, this is AX2, which is actually a configuration that is associated with a linear shape. So A is the central atom, but where did the two come from? Notice that there are two structures attached to the central atom. There are two atoms attached to the center. So therefore, the 2 subscript comes from these two. Notice that there are no lone pairs, so therefore there is no need to have the E. So these are some compounds with this example right here. So we have trigonal planar. This is the term for the arrangement. And at the same time, this is also a way to describe the shape. Now, if you would notice, the configuration is AX3. So, in the X, you can see that there's a subscript 3. This means that there are 3 atoms attached to the central atom. 3 surrounding atoms attached to the central atom. So again, your central atom is the red one. Let's count the attachments. 1, 2, my mouse won't follow me, and 3. There we go. So therefore, the AX3 configuration is associated with this particular shape. There are some examples. We also have bent-shaped. Now, what do you notice about the bent shape? The configuration. Wait, my head is blocking the way. Oh, my dog wants to chime in. Oh, there we go. The configuration is right there, right there. Okay, so the configuration is AX2E. So this means that to the central atom, there are 2 surrounding atoms attached and 1 electron pair. So if you would notice, again, the X means that there are 2 surrounding atoms, the gray ones. So 2 gray ones attached. And then if you would notice, E does not have a subscript. This means that there is only 1 lone pair of electrons. So if there is no subscript, automatically this means that it has a subscript of 1. So this means that there is 1 lone pair attached to it, and that's why we have the bent-shaped. I remember my joke about E1 again. Anyway, moving on. These are some examples. These are some molecules that are with this particular example. So we also have tetrahedral. So if it's tetrahedral, it means that the configuration is AX4. This means that to the central atom, there are 4 surrounding atoms attached to it. Excuse me. So you would notice this means that there should be 4 gray circles. So if you would count 1, 2, 3, and 4. These are some molecules with this structure. So following this configuration AX4, this means that the shape is tetrahedral. Wait, I gotta move my head again. Abala yung ulo niya, okay. So, how about your trigonal pyramidal shape? So, it has the configuration of AX3E. So, how many atoms are attached to the central atom? There are 3, right? How many electron pairs are there? There is 1. Okay, so these are the following molecules with this particular structure. Let me just move my head back there. Okay. Wait, I'm in the... Oh, we also have the bent shape right here. Wait. I need a better mouse. Okay, so if you would notice over here, you notice that it's a X2E2. So this actually means that there are 2 surrounding atoms attached to the central atom, and then here we can see that there's a subscript for E. This means that there are 2 lone pairs. So with that configuration, it means that it belongs to bent-shaped or V-shaped. So hopefully, at this point, I hope you're getting that what the shapes mean and what do the configurations mean. At the same time, there are different factors affecting the bond angles. So if you would look here, certain shapes will have certain angles associated with them. How do we determine this? Usually these are already pre-calculated and have run through different kinds of tests that are run by chemists. So in a way, these are all theoretical. But at the same time, there are certain conditions that actually show that when the theoretical values actually become the actual bond angles. So it's just to take note of the following conditions. And aside from that, there's a tendency, let me just move my head. There is a tendency for double bonds to actually affect their surrounding atoms. So what happens is that they tend to push single bonded atoms away. So if you would notice here, the bond between the double bond O and the single bond chlorine is greater than the bond between the two single bonded chlorines. Aside from that, lone pairs also tend to affect the surrounding atoms. So in a way, they also tend to push other atoms away. They must have issues. Anyway. So just to sum it up, these are actually, where do I move my head? So these are actually the shapes and the angles of the electron groups. So when you do the practice problems, it would be best to refer to this particular table. So even when you do the activities. So again, there is no way to compute for the value of the angles right now, but it would be best to take note that we have a table here that summarizes it. So let's start with the following ones. So here we have methane. So if you would look at methane, what is the central atom? So your central atom is your carbon. So here we have X4 for our Axeman configuration. Where do we get the 4? From the hydrogens attached. And because there are 4 hydrogens attached, this means that the code is AX4. And if we would go back, AX4 is actually associated with being tetrahedral. And the angles will always be 109.5 between each other. So, what's important here? You need to be able to determine the Axeman configuration. And upon determining the Axeman configuration, you can have an idea on what the molecular shape is. So here we also have your ammonia. Look at ammonia. The configuration will therefore be A for the central atom, X because of the 3 hydrogen atoms attached to it, and finally 1E. And this is actually associated with being trigonal pyramidal. So there are actually more problems here. I'd like to skip to this particular one. So in this particular part, we actually note that we treat this particular carbon as the central atom. And after doing that, we count the number of attachments to it. So we count this hydrogen as 1, and then we count this particular structure also as 1. So therefore, there's a total of 2 structures, 2 atoms attached to the central carbon right here. In the same way, we do this for the other carbon, treating this as our second central carbon. So with that, we have 1 atom attached to it and then another. So think of it this way. Here, we end up having 2 Axeman configurations. And either way, they are both linear. So these are actually some more examples that regardless of the arrangement of the Lewis structure, you would notice that they still have similar shapes. And that just to take note that as the formula get more complicated, as the molecules get more complicated, of course the structures are expected to be bigger and also more complicated. However, for the larger structures like proteins and carbohydrates, generally your macromolecules, the VSEPR theory is a bit more difficult to apply because they are so big. So in a way, it's difficult to actually determine which is central. At the same time, because there are so many atoms attached to it, it becomes very difficult to determine the angles because it depends on what is your central atom. So in a way, we will be trying to apply these concepts only on smaller molecules while you're taking general chemistry. So this is the end of our slide. Hopefully this will help you, and hopefully it isn't too long. But anyway, if you have questions, just feel free to email me, and I will see you next time. Bye-bye.